Welcome back to the ICND1 video series, and in this video we'll be looking at the IP protocol. Okay, so from the previous video we know that at the data link layer there are protocols such as Ethernet, token ring, frame relay, HDLC, PPP that allow devices in the same network, whether they're in the same local area network or the same wide area network, allows devices to be able to communicate, share information and share resources. So with Ethernet, devices will all connect to an Ethernet switch, so they're all part of an Ethernet-based network. And Ethernet says that any devices which connect to the Ethernet network are able to communicate and share resources. However, layer 2 protocols don't define how devices in different networks, whether that be different local area networks or different wide area networks, Ethernet doesn't define how those devices are able to communicate and share resources. Essentially, these layer 2 protocols don't define how to interact with other layer 2 protocols. So in this case, Ethernet doesn't define how devices in an Ethernet-based network can communicate with devices over a frame relay-based network. There has to be some other protocol which allows devices, regardless of what kind of network they connect to, regardless of what layer 2 protocol is running on that network, there has to be a protocol which allows interoperability and communication between devices in different networks, and that protocol is IP. So with IP, it defines a set of rules for devices that connect to an IP-based network. It defines how they are able to communicate and share resources. Now IP rides above the data link layer, so essentially it avoids all the layer 2 details. It says it doesn't matter what kind of layer 2 network you connect to, what kind of layer 2 protocol you are running, as long as you have an IP address, you're able to communicate with another device that has an IP address. It doesn't matter if you connect to a token ring network, or they connect to an Ethernet network, or if they connect to some sort of frame relay or MPLS based network. So with IP, the device A, which is using the Ethernet protocol, device B, which is connected to which is running frame relay at layer 2, those two devices are able to communicate as long as they have IP addresses. So the main point we want to take away from here is that at layer 2, devices in the same network are able to communicate. However, these layer 2 protocols don't define how devices in a different network or devices that connect to a network running a different layer 2 protocol are able to communicate and share resources. Instead, it's IP, because IP says it doesn't matter what kind of network you connect to, what kind of layer 2 protocols you are trying to use in your LAN or WAN, as long as those devices have an IP address, they're able to communicate and share resources. And the reason why we have different layer 2 protocols is because these layer 2 protocols are specialized for the kind of network that the devices connect to. So as an example, Ethernet is specialized for LANs. However, Ethernet wouldn't work too well on wide area networks. The reason why? Because Ethernet sends broadcast. Remember, with a wide area network, hundreds or even thousands of devices can connect to the wide area network. And if they're all sending broadcast messages, that causes too much traffic to be in the links and causes saturation and the bandwidth to just all be used. And also, we don't want our devices to send broadcast messages to each other, because that exposes a security risk in that devices from Google will be sending broadcasts to devices from Facebook. And enterprises will be able to find information about each other from those broadcasts. So instead, we run protocols such as MPLS and frame relay on WAN networks, which say that it allows for communication, but it's also specialized for those type of networks. As an example, with frame relay, no broadcast messages are sent. Instead, only unicast messages are sent, and unicast flow from one device to another device, making sure that traffic only flows between the correct enterprise sites. So because we can't use the same layer 2 protocol across the world, we have to have interoperability between those layer 2 protocols, which is defined through IP. IP says no matter what layer 2 protocol you are running, devices are able to communicate as long as they have an IP address and follow the IPv4 protocol. So IP essentially allows for end-to-end communication. It allows for devices in different networks running different layer 2 protocols, allows those devices to be able to communicate, share resources and share files. And packets are routed based on the destination IP address of the packet. So the source IP address is the IP address of the device sending the data. The destination IP address is the IP address of the device that should receive that data, that packet. So all routing is that when we want to communicate with a device in another network, in another LAN, we send that packet, that data, to our router. Now our router has a connection to a wide area network, and if that wide area network is able to reach another LAN site, so maybe this is another enterprise site. This is the device that we want to reach. So device A wants to communicate with device B. The device A will put its IP address as a source IP address, and it will put the IP address of device B as the destination IP address. That packet is forwarded to the router. All routing is just the process of sending that packet to different routers and between different networks, so that that packet gets to the correct destination IP address. So that's all routing is. So with routing, we have router 1, router 2, router 3, router 4. Host A would send that packet to router 1. Router 1 will send that packet to router 2, router 2 to router 3, and router 3 to device B. That's called routing because essentially each of these interfaces on the router represents a different network, a different broadcast domain. Because it represents a different network, we're essentially forwarding the packet through multiple networks until we get to the correct destination device. The IP address is also used to define whether that destination device resides in the same network as us or in another network. So in this case, even if devices connect to the same network, they have to have an IP address. And so the way it works is that when a device wants to communicate with a device in another network, we ping that, we can say, okay, we're going to send data to to the IP address of device B. Device A will actually look at the IP address of device B, and using some sort of maths, it will be able to calculate and find out whether device B lives in the same network as itself, and if that's the case, is able to send that packet directly to device B. If it, in this case, as an example, let's say device A wants to communicate with device C, it can look at the IP address of device C and determine whether or not that device is in the same network as itself. If in this case it wouldn't be, so it knows that to communicate with the device, it has to send that packet to its default gateway, its router. Now that's why all of our devices have to have an IP address, because it's the IP address which tells a device whether that guy he's trying to talk to, whether that device is in the same network as itself or in another network. So let's look at the IP header format, we don't need to know all of what these fields mean at the moment, but the four fields I want to focus on are the time to live field, the protocol field, source IP, and destination IP. So like I said before, the source IP just defines who is sending this packet. The destination IP address just defines who's the recipient, who this packet is intended for. The protocol just identifies how we're sending this IP packet, whether we're using TCP or UDP. The time to live field is used to break what's called a routing loop. So in the previous slide, I talked about how all routing is forwarding traffic between networks to make sure that that traffic gets to the correct destination device, and it's the process of forwarding traffic between networks so that devices in different LANs are able to communicate and share resources. So with a routing loop, if for some reason a router starts going crazy and can't process packets properly, or if some routers have an incorrect route, or if some sort of link breaks which causes a routing loop. In any case, if a routing loop is caused, what a routing loop is it's a packet that loops around endlessly in some sort of circle, in some sort of loop, which saturates our links and causes too much traffic to be on our links, which can make our network slow, can make the performance of our network terrible, and our devices will be busy processing that packet because it's continuously looping around, meaning it doesn't have enough resources to process the other packets. Now the time to live field essentially breaks this loop. So what the time to live field says is that when a device first creates an IP packet, so when device A first creates an IP packet, it sets the time to live field to 255. Send the packet to this router. When this router receives it, when it forwards on that packet, it decrements the time to live field by 1. So in this case, it'll be 255. When this router sends it to this router, it'll be 254, then 253, then 252. So essentially, each time a router forwards on a packet to another router, it decrements that time to live field by 1. Now, if that time to live field is decremented all the way to 0, it means that this packet has essentially, its lifetime has expired, and that packet needs to be discarded and dropped. This stops a routing loop. So in this case, imagine that this packet we're sending, device A was sending, loops around this network, and it gets back to here, and it has a TTL of 1. When this router, let's say router 1, looks to forward this packet onto this device, it sees it's got a time to live of 1, decrements by 1, which leaves a time to live for the 0. It knows that the life of this packet has expired. This packet is no good, so it's going to drop it. And essentially, this breaks the loop and stops stops the packet from looping around endlessly, causing trouble in our network. So IP delivers packets to our network based on a best effort delivery service. Well, that means that the IP doesn't guarantee that the packets will get there. It says that it's going to try its best to ensure that the packets get there, but if they don't get there, then that isn't his problem. Okay, so you have device A and device B. IP doesn't promise the applications running on device A or device B that it can guarantee that packets sent from device A will always end up at device B, or whether if packets are dropped, it's going to resend those packets. Instead, IP relies on the transport layer to provide those functions. So the transport layer, such as TCP and UDP, will provide reliability, set up a connection, drop packets. IP just says, as long as you feed me data, I'm going to try my best to get that data there, but if it doesn't get there, then it isn't my fault. There has to be some other sort of mechanism to deal with those issues. And IP doesn't deliver the data in any particular order as well. Again, that's left up to TCP. It says that as I receive that data from the application, I'm going to send it, even if the data isn't in the correct order. It's up to something at the application layer. It's up to the transport layer to reorder that data in the order that it was sent, so that the application can process that data in the correct order. So like with the Ethernet protocol, with the IP protocol, we have to give our devices an address so that we can uniquely identify each device. So with Ethernet, we saw that we give devices a MAC address. So the MAC address is assigned to a device when it's first manufactured, and essentially is a globally unique address which identifies that device. So in this case, device A would have a MAC address, and device B would have a MAC address. And when these two devices wanted to communicate, let's say device A wanted to send some data to device B, device A would set its MAC address as a source and the destination MAC address of device B. So then now the switcher knows that this packet came from device A and is going to device B. Very similar, we have to give all of our devices an IP address. And an IP address is just a logical address. So by logical, I mean that we assign the IP address. It's different to the MAC address in that the MAC address is a physical address. It's burned in to the actual device itself. So it's on the motherboard. It's on the network code of the device itself. We can't change it. With a MAC address, with an IP address, sorry, it's configured in software. So in this case, when you go into your operating system, you might configure an IP address in software, or you might obtain an IP address from DHCP, which is stored in software. So because the IP address is a logical address, it means that it can change every day. The IP addresses of a device is always changing. And it also means that we can easily move our devices between networks and change what kind of IP addressing we use relatively easily. It doesn't take much of an effort. And to be honest, the most important thing about IP addresses is that it allows us to logically group devices together. So with an IP address, a certain part of the IP address represents the network, and then the other part of the IP address represents the host on that network. So in this case, imagine that this is an IP address of one of the devices on our enterprise network. Let's say the first three numbers represent our network, and the last number represents that device in our network. So what that means is that any device in our network has to begin with this combination of numbers in the IP address. So when we assign IP addresses to all the devices in our network, this is our building, these are all devices, their IP address all have to begin with these first three numbers. And that makes it easier for our WAN SPs and for our ISPs and for people all over the world to communicate with us. So with a router knows how to reach different networks because it has a routing table. In essence, a routing table is just a table listing routes to reach different networks. And so this makes it more efficient because now the routers in the internet, the routers in the WAN network know that to reach all devices in our enterprise, to reach all devices that begin with these first three numbers, forward all traffic to over here. So in essence, to reach, let's say, 255 devices or 300 devices or 400 devices or 100 devices, they know to reach all those 100 devices, they can send traffic to what's called to this root here, so they can use this root. So in this case, in the routing table, the root will look something like this. It will list 192.168.1.0, and it essentially means to reach any devices that have an IP address that begins with these first three numbers, you can use this route. So in essence, we can reach 100, 200 devices by using a single route. So with an IP addresses, they follow a hierarchical structure in that they all begin with the first few digits, and by that it makes routing more efficient. Now let's say the IP didn't allow us to logically group devices together, or it didn't enforce that devices had to be logically grouped together. What that means is that we can have devices all over the world that begin with these first three numbers. And what that means is that these routers would have to have a route to each device. And imagine, and the thing about how many devices that we have in the world, there's billions of devices in the world, millions and billions of devices in the world. That would mean these routers would have millions and billions of routes, which just isn't feasible. The routing table would be too large, and trying to get traffic between one network to another network would be too slow, because the router would have to search through this massive routing table. I mean, at the moment with this logical addressing, the routing table for the internet is at 400,000 to 500,000 routes, which is massive, and this is with all this efficiency of grouping devices together. So with IP, it allows us to group devices together because a certain part of the IP address identifies the network, and instead of having a route to each device, we can have a route to the network. So the routers in the internet would know that all devices that begin with these first three digits reside in this building. So in essence, instead of having to have a route to each device, there could be 100, 200 devices in that building. Instead of having a route to each device, the router itself could instead just has a single route, saying that to reach this group of addresses, to reach devices that have these first three numbers as their IP address, I can just use this single route. I can just use, so in the routing table, it lists one route instead of having to list multiple routes for each destination device. So let's look at the format of an IP address. So an IP address itself is 32 bits in length and consists of a network port and a host port. Like I said in the previous slide, the network port just identifies the network the device resides on, allows us to group devices in the same network together logically, making routing more efficient, and the host port just identifies that particular device in that network. Now the IP address is split up into 4 blocks known as octets, and each octet is 8 bit long. So essentially, if we get this 32 bit in length IP address, we split it into four chunks. Each chunk is 8 bits, and each of those blocks is known as an octet. So in this case, this is one octet, this is another octet, this is the third octet, and this is the fourth octet. So each of these octets is 8 bits in length, which means that each octet can have a value between 0 and 255. So essentially, when we do the conversion to binary, we will see what that is. But just for now, each octet can have a value between 0 and 1 and 255. So in this case, this could be 200, 223, this could be 225, this could be 0. And so, it's called an octet because it's made up of 8 bits. So, like I said before, there's a certain part of the IP address which represents the network that the device resides in. Now, how do we know? So, how do we know what part of the address represents the network and what part of the address represents the host? It's because when we configure an IP address, we also configure what's called a subnet mask. A subnet mask also consists of 4 octets, and so the most basic logic with a subnet mask is that if an octet in the subnet mask is a 255, it means that the same octet in the IP address represents the subnet mask. So in this case, the first octet of the subnet mask is 255, so is the second, so is the third. That means that these first 3 octets of the IP address represent the network that the device resides in. If an octet has a 0, it means that the corresponding octet in the IP address represents the host. So in this case, the first 3 blocks of the IP address match up with the 255 in the subnet mask, meaning that the first 3 blocks represent our network. The last block of the IP address matches up with a 0, which means that this last block represents our device within our network. So it's used to uniquely identify our devices within our network. So it's a subnet mask which actually identifies what part of the address represents the network and what part of the address represents the host. And so the most common subnet masks are 255.0.0.0 and 255.255.0.0. So in this case, with the first one, only the first octet represents the network, and all the other octets represent the host, which allows us to have more hosts. With this one, the first two octets represent the network, and the last two octets represent our host. So as you can see, we can have varying different subnet masks so that we can define what octets represent our network, and essentially the octets that don't represent our network represent our host. And by having smaller subnet masks, it allows us to have more hosts within our network. Now, like I said before, the IP address itself is 32 bits in length. And so when humans, or when we look or write IP addresses, we always write IP addresses in decimal format. With computers and PCs and laptops and switches, they read the IP address in binary. So essentially, we need to know how to convert from binary into decimal, so that we for what's called subnetting math. So when we want to subnet our IP addresses, that's talked about in a later video. But essentially, we need to know how the computer views and looks at the IP address, so that when we subnet, it makes it easier, and so that we can understand how to subnet a IP address properly, so that the device can read it and understand. So to convert from binary into decimal, we know that binary follows powers of 2. So in this case, 2 to the power of 0 is 1, 2 to the power of 1 is 2, to the power of 2 is 4, 2 to the power of 3 is 8, and so on. And we know that each octet is 8 bits long. So all we do for each octet, we write a table of all the powers of 2 up to 2 to the power of 8. So in this case, 1, 2, 4, 8, 16, 32, 64, 128. And then what we do, let's say we get this number here, we just put a 1 underneath each of these numbers until we can get to our decimal. So in this case, we have to look at this in a way in that we have to think about this in that how do we get that number. So in this case, how do I make up 192 from these numbers that I have available to me? So to make up 192 is simple, it's just 128, 64. So I put a 1 in the numbers that I need to make up this decimal number, and I put a 0 in the numbers that I don't need. So 1 means yes, I need them, add them together. 0 means no, I don't need them, don't add them together. So in this case, 128 by 64 equals 192. So 192 in binary is 11000000. 168 in binary would be 128 yes, 64 no, 32, so 128 by 32 is 160 yes, 16 no, 8 yes, 4 no, 2 no, 1 no. So 168 in binary would be 10101000. As you can see, trying to convert from binary into decimal is very, very simple. All we do is that we write this table. So every time we want to convert a number into binary from an IP address, we write out this table, goes up in powers of 2, up to 2 to the power of 8. And underneath each number, if we would need that number to make up this decimal number, then we put a 1. If not, then we put a 0. And then once we've written out, that would be our number in binary. So 168 in binary would be this. This is 168 in binary. Example 10 in binary would just be 0, 0, 0, 0, 8, 0, yes, yes. So 10 in binary would be 0, 0, 0, 0, 1, 0, 1, 0. You can see converting from binary to decimal is very, very simple. IP also defines what's known as classes of IP addresses. So when I was talking about a subnet mask, I was saying how a subnet mask can be used to define how many devices we can have in our network. So essentially, a subnet mask which has 1 to 55 can have more hosts than a subnet mask that has more to 55. So what I'm trying to say is that we can see from these subnet masks here, the most common ones, 255.255.0.0 and 255.255.255.0. So as you can see, with this first subnet mask 255.0.0.0, we can have more hosts than if we use this subnet mask with a network or this subnet mask with a network. The reason why is because more numbers in the IP address represent the network, leaving less octets available to identify the host. Now with IP, we can't just use, with the original rules of IP, we couldn't just use any subnet mask with any IP address. Essentially, there were specific IP addresses that we could use specific subnet masks with. And so by using a variety of different subnet masks, it allowed us to accommodate networks of different sizes. So essentially, very large networks would use this subnet mask, medium-sized networks would use this subnet mask, and smaller networks like your home network or a small office, home office, would use this subnet mask. And like I said, we couldn't just use it with any IP address. Essentially, we had to use a specific IP address in order to use these specific masks. And so this is what we call classes of IP addresses. So in essence, class A addresses make use of the subnet mask 255.0.0.0, which allows for 16 million hosts per network. So these are for very large enterprises. The only problem is there are only 126 networks in the world which can use this subnet mask. So with Class A networks, Class A networks have to have a first octet value of 0 to 126. So if we see an IP address and in the first octet, so in the first block, it has a value from 0 through 126, it means that that's a Class A address. Class A addresses are for very large networks. There's only 126 Class A networks available to use. However, those networks can have 60 million hosts per network. Class B networks are slightly smaller in that they use a subnet mask of 255.255.0.0, but they still allow for 65,535 hosts. These would be used for your medium-sized businesses. And so with Class B networks, they have a first octet that ranges from 128 through 191. So if we look at an IP address and we see the number 130 in the first octet, it means that that network is a Class B network. Class C networks are smaller than Class A and B networks because they use a subnet mask of 255.255.255.0, which means that the first 3 octets represent our network. These are for small offices or for your small homes. Now, there are over 2 million Class C networks available, but each network can only support 254 hosts. So essentially, with a Class C network, the first octet has a value from 192 through 223. So if we see a network, an IP address with a value of 200 in the first octet, we know that it belongs to a Class C network. So with the different classes, we can have more hosts or less hosts depending on the size of a network, which allows us to accommodate all sizes. Now bear in mind, these classes of IP addresses were designed when IP first came out. Over time, what's a feature known as variable length subnet masking came out, which essentially allowed us to use any subnet mask with any IP address, allowing us to cater to the needs of different businesses. So the way it works is that we could use a subnet mask which fitted our needs. So instead of following these guidelines of 255.255.255, we could essentially use a subnet mask like this. 255.128. Which essentially means that we can have that with a subnet mask, we can have about 126 hosts within our network. So we could create custom subnet masks, allowing us to create a network big enough for how many users that we have, regardless of whether we use Class A, B, or C addresses. These classes of addresses were originally designed when IP first came out, and were originally designed to cater to different network needs. But we'll talk about variable length subnet masking and subnetting in general in a later video. We also have Class D and Class E networks. So Class D networks are used for multicast. So Class D IP addresses are used for multicast, and they have a first octet which ranges from 224 through 239. All multicast is a group that devices can join, and as long as devices are part of that group, any data sent to that multicast address, those devices will receive. If a device isn't part of that multicast group, then traffic sent to that multicast address will not be received from that device. Class C is used for experimental use. So Class C IP addresses range from 240 through 254, and they can't be used as IP addresses that we assign to our devices. So Class D and E, we can't assign those IP addresses to our devices. Now, the address range 127 through 127.255.255.255 is reserved for loopback testing. All loopback testing is, it allows your device to test its network functions to ensure that its network interface card is working, and to ensure that all the processes are working that it needs in order to send data to a destination device. And with IP, the address ranges for each class of network were chosen because those address ranges for those certain classes all have something in common. So with Class A networks, all the numbers in the Class A network, so 0, 1, 2, 3, 4, all the way up to 126, they all begin with a binary 0. So in this case, let's say we convert 126 to binary. Essentially, 126 in binary would be, I think, 0, 64. So 126 in binary, I'm not going to do calculation completely, but 126 in binary would be 0, 1, 1 something. So essentially, what I'm trying to say, the address ranges for each class of network were chosen because those particular series of numbers, those particular range of numbers all have something in common. So with Class A networks, they all begin with binary 0. With Class B networks, they all begin with binary 10. And with Class C networks, they all begin with binary 110. So, like I said before, the computer itself reads IP addresses in binary. So when we write down an IP address, it's able to identify whether that IP address is a Class A, B, or C network based on the first few binary digits. So based on the first few binary bits in the first octet of the IP address. And so that way, the computer is able to see whether the IP address is in a Class A, B, or C network and auto-generate the correct subnet mask based on those Class A, B, and C rules. Now, within our network, there are two specific IP addresses that can't be assigned to any devices on our network. Like I said before, with our IP address, the first half identifies the network, the second half identifies the host on the network. As an example, these two IP addresses for this network couldn't be assigned any of our devices. This is the first IP address and the last IP address. The first IP address is used to identify that network itself. So like I said before, IP allows us to logically group devices in our network. And all devices in our network are identified by using this IP address. This essentially identifies our network. This says that if you want to reach any devices in this network, then you can use this route. The last usable IP address is known as the broadcast address and is used to send packets to all devices in that network. So essentially, when you look at routing tables will list the first IP address of the network in the routing table, which says that to reach devices in this network, you can use this route. The last usable IP address is just used to send broadcast packets. So normally, any IP address with a 0, don't use. Any IP address with a 255, you can't use. That's not always true. So as an example, if we were to draw a Class A network, this is the first usable IP address. We couldn't use this to assign devices. However, this IP address we could use, because even though it's got zeros in it, this isn't the first IP address of this Class A network. And in the case, this would be the last IP address of this Class A network. So with IP, the first and last IP addresses cannot be used because they are reserved for special purposes. The first IP address of a network is reserved to identify that actual network itself, and the last IP address is known as the broadcast address and is used to send a packet to all the devices on that network. So within IP, there are what we call public and private IP addresses. Private IP addresses are IP addresses that we can assign devices in our network, in the same local area network, and those devices are able to communicate. Public IP addresses are devices that we assign to devices when they have to access the internet. So in essence, with public IP addresses, we could assign devices in our network private IP addresses and they'll be able to communicate with each other. However, with those private IP addresses, they won't be able to access the internet. Now what that means is that we can have two buildings which are separate from each other, and we can assign those devices the same private IP addresses. And as long as we only need communication within our own network, that works fine. So these devices are able to use the same private IP addresses as devices that in this company, and they're all able to communicate within their own local area network, with their own LAN. However, as soon as we want to access the internet and access resources on the internet, these devices have to have what's called a globally unique public IP address. A public IP address is globally unique, so no two devices would have the same public IP addresses, but devices can have the same private IP addresses. And with the public IP address, when is used to access the internet, it's a globally unique IP address, which means that devices, when they access the internet, no two devices can use the same public IP address. But as you can see in our example, devices can use the same private IP address, and that's what's used. So if you look at your home network, most home networks use the same private IP address. The reason why is because it doesn't matter. If it's a private IP address, it's only supposed to be used within the same local area network. So devices in the same local area network, they can use the same private IP addresses as devices in another local area network, as long as those two local area networks have no connectivity to each other and don't access the internet. And so within IP, there are a special range of IP addresses which have been reserved for private use. So essentially these addresses can only be used as private addresses and cannot be used when we access the internet. So for class A is 10.0.0.0 through 10.255.255.255. For class B is 172.16.0.0 through 172.31.255.255. And for class C is 192.168.0.0 through 192.168.255.255. And so those are the private address range for class A, B, and C networks. So we reached the end of this video, and we looked at the basics of the IP protocol, how the IP addresses are used and what they're used for. We've looked at what IP actually allows. It allows devices in different networks to be able to communicate, no matter what latest protocols are running on those networks. And we looked at the different classes of IP addresses and why they were created by the creators of IP. So the different classes of networks just allow IP to support networks of different sizes, so very large networks, smaller networks, or even very, very small networks. And we talked about what private and public IP addresses are used for. Private for local area communication, public for communication over the internet. And we talked about that there are a certain range of IP addresses for each class of IP address, so class A, B, and C. There are certain ranges of IP address which are reserved for private use only. I hope this has been informative for you, and I would like to thank you for viewing.